Hello again, problem solvers. We are going to work on algebraic manipulation, which is lesson 14. And I'm expecting you to have the ice sheet in front of you somehow, whether the Word file on your computer or print it out. But I'm going to just kind of talk through the problems and show you how to do them. There are 4 on this ice sheet, the problems for class. And the first one is to find positive integer solutions, x and y, to this thing. And so normally you were told in pre-calculus or in Algebra 2 to move everything to one side, set equal to 0, set each individual thing to 0. That doesn't work here because it doesn't factor that way, but it does factor like this. What you can't do, it's easy to set each thing to 20, but that is illegal. That only works if you're equal to 0. But we know x and y have to be positive integers, and so you also know that x minus y then would be less than x plus y. And you know that these have to be factors of 20, the way it's written. So 1 times 20, 2 times 10, 4 times 5, those are your only options. You can't go the other way because this one needs to be smaller. Okay, so if you try to solve these equations, and you can do this with Gaussian elimination, which is just adding the equations. You probably don't remember that phrase, but you probably remember doing this. 2x equals 21. Well, x would be a fraction, but x is supposed to be a positive integer, so that's no good. If we try 2 and 10, you get 2x equals 12, so x is 6. Y would be 4. That works. And lastly, if you do 4 and 5, you get 2x equals 9, and that makes x not an integer. So this is the only pair of integer solutions for that equation. Alright, so it's tempting to try to do this next problem the same way. And it kind of is, requires a little bit of a variation. The next problem says find 3x squared y squared if you have this equation where x and y are integers again, so same idea as before. But you have this equation, 30x squared plus 517. Okay, you see that 3x squared y squared is what you want, so it's tempting to just solve for that, but we're trying to get an actual number, so we want to factor. And again, they give you that x and y are integers, so that makes me actually want to use what I did in the previous problem and move everything but 517 over here and try to set it equal to 517 and then think about factors. So this does factor. It takes a bit of playing with it. It doesn't factor with x and y like the previous problem. It factors with x squared and y squared. And if you think about it that way, 3x squared and y squared would have to be this guy, and everything kind of falls in place after that. You need a minus 10 here, and you need plus 1 here. Except I cheated. I didn't do the middle part. I just did the last and the first, right? So let's double check this. Put a question mark here. 3x squared y squared plus y squared minus 30x squared minus 10. I guess I really didn't do the L. I did everything else. Okay, well then that means that if I subtracted 10 up here to make this work, I should subtract 10 over here. So if I put 507 instead, I'm just tweaking this to make it fit, that actually works out. So the problem says that this factored thing, I borrowed 10 from the other side, so this is actually equal to 507. So this is wishful thinking, right? I factored it the way I wanted it to factor, and then I went back and got the constant I needed. Okay, so now I can think about factors, and 507 is, if you have an old copy of this sheet, it was incorrect before. It's 3 times 13 squared, not 3 squared times 13. So 3 times 169, and if you have these two guys here, x and y are integers, so you need to check, is that against 3, is that against 13, and so on, and which ones give you x and y to be integers, and it's kind of convoluted to work out. But I'll go ahead and work out this a little bit. The only options are 3 times 169, or the other way around, or you could do 13 times 39, or 39 times 13. I guess you could do 1 and 507, but I'm a little suspicious. Definitely couldn't do 1 over here because x needs to be positive. All right, so if you work these out, you can tell that 3 doesn't go over here because then you would, when you divide by 3, you'd be taking square root of some crazy thing. So it's not that. Likewise over here, you can quickly see, you don't need to do the whole thing out. Square root of 13, if you set those equal, that's no good. Okay, so same thing here. If you did that one, you'd subtract 1 and get 38 over 3. That doesn't make sense. Okay, so let's try this other one. If you did this one and set these equal, you'd have 3x squared plus 1 equals 13. Subtract 1, you get 12. X squared equals 4. And I don't know if x is plus or minus 2, but I don't care because I just need x squared for that expression up top. And then y squared minus 10 equals 39. Add the 10 and you get 49. And again, I don't care if it's plus or minus 7. So these go back up here. That's 4. That's 49. So 3x squared, y squared, all together, you multiply all those out, you get 588 as your final answer. Don't forget to do that part of the problem. All right, so the third question here is to show that this number is composite no matter what n is, as long as n is an integer. So n to the 4th minus 20n squared plus 4. Okay, we are again going to use wishful thinking. This does not factor. But if it did factor, pretend you're just thinking about in general, what does this look like? Well, think about something that looks like this. So do some wishful thinking off to the side. If you have x squared plus bx, actually let me put a minus here. Like I want to match what we have over there, which is a subtraction sign. So minus bx plus we'll just put 4. We'll just match what's going on here. That would be something like x minus 2, x minus 2, right? Because you get the plus 4 and you get negative, negative. Something like that. So we have double powers, right? We have to the 4 squared and so on. But we wish it looked like something like this. So I guess here that would be 4x, right? So let's do the same thing here. N squared minus 2, n squared minus 2. This is what I wish was true, right? That would work for all the terms except the middle. What that really is n squared minus 4n squared plus 4, right? It kind of looks like this. So, but we don't have that. We have this minus another 16n squared. Okay, so my initial thinking convinced me to split that middle term in a way I maybe wouldn't have thought of otherwise. And now let's go back and do this. Based on the line above, this is n squared minus 2 quantity squared. And this is 4n quantity squared. The reason I'm doing that is because now this is a difference of squares. So you take the first one minus the second one, and then you take the first one plus the second one. Okay, so now I've factored it into two integers. If n is an integer, so are these. And that makes this whole big thing composite. So this line, let's throw that out. Every other line is equal. Okay, those are all the same expression. This was part of my wishful thinking. All right, so that's the third one. This last one's a bit of a doozy. It's okay if you don't get to do it on your own. So, because there's a key fact here that you maybe wouldn't have thought of, but you'll know it after I tell you. So show that for no positive integer n, can both n plus 3 and n squared plus 3n plus 3, those cannot both be perfect cubes. And what I mean by perfect cube is that it's an integer cubed. So 1, 8, 27, what's the next one? 4 cubed is 64, 125. Those are the perfect cubes. Okay? And you can see they grow farther and farther apart. That's important. Okay, so if they are both perfect cubes, then their product would be as well. So think about if this was, if you have a cubed and b cubed, well then a cubed b cubed would be the cube of ab. Okay, so that's the first kind of weird trick. If I multiply these, it should still be a perfect cube. So this is by contradiction. Suppose they're perfect cubes, and their product is as well. And then let's multiply that out. We're going to use the good old distributive property. I'm going to write the final version, so you should do the algebra and make sure you get this. What you notice here is that this almost factors, but the 9 messes you up. If this was 8 plus 1 for the 9 here, this is n plus 2 quantity cubed plus 1. So perfect cube plus 1 would be another perfect cube. Look at these perfect cubes. They go farther and farther apart, and they're never one apart. So that's the contradiction. Perfect cubes cannot be consecutive integers unless one of them is 0. 0 and 1 are one apart, but these are not. Neither of these are 0, because n is an integer. I think it's actually a positive integer. Yeah, positive integer. So that's not 0, and then that's not 0 either. Okay, so by contradiction, these cannot both be perfect cubes. That one's tough because you have to reference a lot of facts that maybe you wouldn't have thought of, but now you have them. All right, so that's it for the ice sheet for algebraic manipulation.